So Mr. Schwarz will talk about the distribution grid stability. He is currently chief engineer at the Institute of Professor Monti, automation of complex power systems here at the E.ON Center. That being said, I give you a word. You have a microphone. Yeah, please go ahead.
Thank you. Okay. Good. Yeah, thank you very much. Thank you for the kind introduction. So title of my talk, Distribution Grid Stability Beyond 2025, Will Voltage Become the New Frequency? So as a motivation of my talk, basically what I did a research. I looked into different reports, literature, documents from well-known actors in our field like SIGRE, Bundesnetzagentur, ENSUI, ETSO, and was interested in their perspectives on voltage control and stability. And interestingly, if you look at how they see the role of voltage control and stability, you somehow feel that it's for them kind of a secondary type of role, here formulated by this quite provocative type of statements. Yeah, you read something like that frequency is basically the main stability metric and just voltage is a local concern. That in general voltage issues, they just occur in weak grids. That we have established components like OLTCs or shunt compensators in order to tackle voltage issues. And that everything that basically we do in software when it comes to voltage control is considered as a workaround. However, you can also see that the latest report is from 24, and I believe opinion changed with an event that happened that year. I think you can already guess. It was the blackout, unfortunately, that we saw in April this year in Spain and Portugal. Investigations on this blackout are still ongoing, but at least we have some reports available by the Spanish operator and by an ENSUI working group. And it can already be concluded that, in fact, this blackout was due to voltage, in this case, over voltage issues. So to shortly recapitulate what has happened in Spain, basically on the 28th of April, there were oscillations in the system. Oscillations, they can either be forced or natural, and they also happened on this day. However, operators are usually quite aware of these oscillations and they know what to do. So also on that day, and what they did as a measure against this voltage stability issue is that they reduced the impedance of the system and they reduced active power because they were in a generating state to the neighboring countries, so basically France. That of course mitigated and stopped this oscillation, but it came with side effects. The first one was that because you have a reduced impedance, automatically your voltage in the system increases. And because you are exporting less active power, that also means for your generators, of course, locally that you have in the system, that you have to generate less active power. Now, it's the issue that most of the generators on the local level, so basically PV and wind, if you decrease the active power because they operate typically on a fixed P and Q type of control, you also automatically reduce the capability to provide or absorb reactive power. In this case, because we were generating, they were all in an absorbing state. So that also led again to a rise of voltage. Then basically two things came on top. The first thing was that some of other larger generator plants, they were not really following the grid codes when it came to dynamic voltage control. And in the distribution grids, as they were not so well monitored, there were actually overvoltage that were not detected. It looked quite nice from the, let's say, transmission perspective, but in the distribution grid, voltages started increasing. And they increased and increased until at a certain point, first generators started to trip. Now remember, they were absorbing reactive power. When they tripped, also you will lose again this capability, voltage rise again, and so on. It's a cascading effect until really at the very end, the system, the pointer, basically the voltages were extremely high and the system collapsed. So the main takeaways from this incident basically is that in such extreme events, we see that voltage control based on classic static PQ might be too inflexible. It's difficult to see what devices are really doing in the field. So maybe they are following grid codes on paper or in the lab, but we don't know how they really behave under operational conditions. And of course, it's unfortunate that we are not really have the capability to really observe what's going on in low voltage and medium voltage. So the point is, we have to think and motivated by this blackout, what is actually the role of voltage in the coming future? Will it be as important as frequency? Will it be even more important than frequency. Yeah, what definitely is clear, different research needs, they lie ahead, yeah, incorporating all the challenges and also requirements that we have today. And here I brought you a picture basically with all the different puzzle parts of yeah, directions that we are working on currently here at the Institute. Of course, today we cannot cover all of them, but I want to give you at least a short yeah, examples of what we are doing in the direction of adaptive voltage control, what we do in the direction of AI and data, and how we can improve real-time monitoring, measuring, sensing, and also testing to really include all the new type of assets and so on that we have in the system. So the grand challenge basically is, yeah, motivated by my previous slides, is that we, at the moment, we are doing basically voltage control in a type of blind fashion, yeah, and according to predefined specifications. So basically really this classical P and Q. So we have to ask ourselves, can we do better? And unsurprisingly, the answer is yes. We have ideas for how we can do voltage control in a dynamic way. And one of the opportunities that we have, for example, is the so-called covariance guided based voltage droop control. What we are doing here is that we yeah, steer the voltage dynamically and basically calculate what are the differences, or in this case, the variances between the local voltages and reactive power in the systems. And also we can learn how at a certain node, if we change the voltage, how this affects the other nodes' voltages and reactive power contributions, and how can we adapt to this basically. So how this works is, you see this here on the bottom. So basically we have data from the grid, so can be classical PMU data that we then use for this covariance analysis part, which us then gives the set points that we need for the different assets. We can write them basically to the inverters that then really can apply them. Of course, the grid will respond to that. Yeah, we go into the loop, measure again, and apply this again. Yeah, advantage quite clear, right? This is an adaptive approach, right? So this means we can react faster to voltage issues and also can make measures against them more efficient. And we have a harmonized type of approach between really the normal operation and fault conditions. Yeah, challenge, it's a more type of advanced approach. Yeah, so that means the implementation effort is higher. We may have a higher computational burden. And it's also quite difficult, at least from a scientific perspective, to prove that in theory no oscillation or instabilities will occur. In particular, if we do this covariance analysis based on a data-driven type of approach, yeah, using, for example, an AI model that we also may need to retrain over the time when things and conditions change. And in this context, one of the things that we can do when it comes to machine learning and learning these models is so-called physics-informed reinforcement learning. Yeah, remember classically you use typically AI when you have data, but you don't have a model. Yeah, but that is different in power systems because typically we have both. We have the data and we have models. Yeah, because there might be existing power flow calculations, state estimation models. We know topology information and so on. So the idea is, why not including this additional information that we have directly into the learning process? So including these physical laws, domain knowledge, topologies, existing models, and constraints. Yeah, unsurprisingly, if we do this, because we add additional information to the model, yeah, our results or the performance of the model is quite good, and we achieve a fast convergence. It's also a matter of trust, yeah, because we are knowing from the physics what is going on in the model, and it's not just as in classical AI models, a purely black box type of behavior. Of course, yeah, again, it's more complex, and we also have limitation when it comes to scalability. We can even bring this one step further and look at distributed type of learning processes using distributed multi-agent type of approaches, which means that we delegate these voltage control for yeah, the different devices as a reinforcement learning agent, basically operating only on local or regional data. And that then in the end can facilitate really decentralized decision making. Yeah, when is this important? Yeah, it's always then important if yeah, different operators or actors have to work on, let's say, a big model that is made up by smaller chunks of the model, yeah, which we typically have in power systems. And one of the opportunities that we have here is so-called federated learning. Yeah, and federated learning, what we are doing is we train a shared machine learning model collaboratively across multiple servers. And we do this in a way that we don't share the data, but we only share weights during the training process. That comes with several advantages that are corresponding to data. Yeah, so we take care of data privacy and compliance considerations. We can ensure data ownership and governance and so on. That also links quite well to the second block that we have today about data spaces. We will hear some interesting talks later. Yeah, challenges, of course, if we do something in a distributed way, yeah, that always means that we have to communicate. And yeah, communication is always, of course, comes with cybersecurity concerns. Another very important point that we have to consider and also is motivated by the blackout is that we typically want to know, okay, what is really going on in the field? So is this PV unit, for example, which is in the real system, doing what it's supposed to do? And one of the ideas is to go beyond power hardware in the loop, what we already know in academia quite well, and to apply this really to the real field. Yeah, so in power hardware in the loop, what you typically have is you have this all in a lab. So you have a real-time simulator, which for you emulates the grid and also can define different test cases. You have a device under test, and you basically look what this device is doing with everything else simulated. Now the idea is to basically have this device under test no longer in the lab, or maybe one component in the lab and others really in the field, using basically communication by means of a distributed co-simulation approach to do this power hardware in the loop setup, let's say, in a fashion where we have not just a single location, but multiple locations. Of course, what we need for this is, again, efficient communication and also knowing how we can really interconnect this. What, of course, here is challenging is then really to establish the full loop, right? Because it's still a different location. Yeah, so in the end, closing this loop is a challenge. And yeah, we also need here persons that are aware basically of both having field knowledge and laboratory real-time hardware in the loop simulation knowledge and bring them together. As an outlook, last but not least, future perspectives on distribution grid stability. I think we all agree that distribution grids in the future, they will play a critical and also new type of role. Not only that we have way more active components in the system together with sector coupling elements and DC technology, but also there will be an emergence of completely new stakeholders and business cases. Yeah, think, for example, about the emergence of energy communities, which in the end leads to more compartmentalization and segmentation type of things in the system. Yeah, so we will have a system, or these energy communities can be considered as a type of a microgrid, and we have multiple of them that somehow will interact with each other. Maybe also different technologies. One of the microgrids can be DC, others can be AC. And interestingly, this trend was so far always going in the direction of frequency stability. Yeah, we did this in order to have frequency stability. And now the question arises with this new paradigm. What will this mean for voltage stability? Will we, when we solve the frequency stability issue, will we then also directly also cover the voltage stability issue when the system is more segmented? And yeah, that is one of the key research challenges that we will work on in the next years, and hopefully we'll find a positive answer. With that, I thank you, and yeah, looking forward later to your questions. Thank you.
Thank you very much. So we will have the questions at the end of both presentations. Sure. And with that, I would like to invite Mr. Herzog, who is Chief Engineer at my institute, to then start with the next presentation.
Okay, yes, thank you very much, Professor De Doncker, for the introduction. I'm going to talk about solid state transformers for power flow control and load reduction in distribution networks. The previous talk focused on stability, and I will now more focus on the loads, the additional loads which occur in today's distribution grids. So here's like a small schematic picture of the classical radial distribution grid, how it has been for the last decades. We have some PV installations here on a few rooftops, and usually the distribution grid transformers are not very heavily loaded, so around 30% or so, which is shown here with the thermometers. And we have normally open connection points between them. So if one grid section, one transformer fails, we can close these switches here and then distribute all the power through one of the distribution grid transformers. The problem is in today's grids, we have a lot of more prosumers. We have charging infrastructure. We have wall boxes at home where everyone can charge with 11 kilowatts. We have heat pumps and we have additional PV. And this faces a lot of loading on the existing distribution grid transformers, and they might even overload. So what is the solution to this? Yeah, we can install a second transformer, right? This is the easiest solution, but I would say it's probably not the best solution because usually, especially in cities, space is very limited. We cannot put at every point a second transformer close to this. Additionally, they are quite large and it needs some time building these. So one option is to use solid state transformers, so basically AC to AC power electronic components. And with this, we can have horizontal power flow between the grids because, for example, the most right grid section doesn't have charging infrastructure installed. It only has some private charging points. So this is probably a higher loading for the transformer because of the PV, because it has to feed back to the medium voltage grid section. So we can transfer using the solid state transformers power from this grid section to the other grid sections which have a higher penetration of electric vehicles, for example. So using this approach, we can use the existing infrastructure, the cabling and the normal open coupling points to then couple the grid sections and have horizontal power flow, which is not possible in a classical AC distribution grid. So what exactly is a solid state transformer? Here in the top right, we can see a classical transformer. It's a very large component. The solid state transformer adds basically power electronics to this transformer. With this, we are not bound to 50 Hertz frequency anymore. And the higher the frequency in a magnetic component, the smaller the magnetic component gets. So we use higher frequencies like 1 to 10 kilohertz, and then we can shrink the transformer and have basically much smaller component here. So this is what we use inside the solid state transformer. The advantage is obviously we need less copper and core material, so the size shrinks much. We have a very high efficiency of the system because this power electronic component is very efficiently because it's soft switched. And also, for example, these isolation transformers are not very efficient compared to the large transformers, for example. And we have a very high power density, which we will see later. The challenges here are that we currently don't have off-the-shelf products. So this AC to AC transformer is not something you can buy at every manufacturer. It's usually some very specific thing which has to be manufactured for the specific use case. Obviously, we have more components. We need the inverters, for example. And at the moment, it's with a higher cost. But that may change in the future because, as we can see, you have a lot of material here in the 50 Hertz transformers. And to show you this, I have a picture here from a former chief engineer of our institute on the left side, 4.5 megavolt ampere transformer from a wind turbine at CWD, which weighs 11.5 tons. And on the right side, the medium frequency transformer in our test hall, which is 5 MVA, so slightly more than on the left side, also for medium voltage, so 5 kV to 5 kV. And here we only have a weight of 675 kilograms. And we can see the density is much higher. So we only need 140 grams per kVA for these solid state transformer or for the medium frequency transformer compared to the 2.5 kilogram per kVA with the 50 Hertz transformer. And we also have a demonstrator prototype at PGS for this AC to AC converter. You can see it in the bottom right or in the schematics in the top. So first we have the rectifier and AC-DC stage with grid side filters. Then we have the DC-DC stage here in our case, the three-phase dual active bridge converter. yeah, the major advantage here is that we can basically use the same topology and the same power electronics here for the DC to DC converter as for the rectifier and the inverter. So we have 4 times the same power electronics components here, and then the medium frequency transformer, which we can see here in the middle. So this is 250 kVA medium frequency transformer for low voltage. And yeah, this is quite small. It's only 50 kilograms, it's switching at 10 kilohertz. And so we have 200 grams per kVA. As a comparison, I looked up one 250 kVA 50 hertz transformer from Block. It weighs 710 kilograms, so much more. And we are at 2.84 kilogram per kVA. It's basically the same numbers as we saw in the previous picture. And we can also see here in the bottom, the LCL filters, they are also quite large in this solid state transformer. Here are the specifications. So the DC link voltage is at 750 volt. We have around 250 kVA of power, as I said, and this is everything is cooled with air. Yeah, and then we can also do some things for controlling this converter. For example, we can do predictive load decoupling. This means that we let the different converters speak to each other. We have communication between the individual controls. And on the left side, we see this without control. So this is what would happen when we just let every converter do its own control. And we can see here that when we do a load step with the DC to DC converter, as we can do active power flow control with this component, that the DC link voltages are dropping down and increasing for the 2 inverter stages with the AC interfaces. And yeah, the reason is that the control is not fast enough. So the control of the DC-DC converter is very dynamic, and the AC-DC converters is mostly limited by the control bandwidth and by the inductive components on the grid side. But if we basically say to our AC-DC converter, hey, load step is coming now, and this is this load step, it can basically use a model to predict which current it has to set. And then we can see here basically a very flat DC voltage and a very dynamic current change. So basically in one step of the control. Yeah, and the question now is, what do we do for new installations if we are already at the capacity of the other grids? Then we can use DC underlay grids here to include, for example, charging infrastructure or energy hubs like central heating and batteries, and also connect like the high loading, like the electric vehicles and the PV, which is causing the difficulties in the AC grid to this DC grid. And this is then DC underlay grid because it's in parallel basically operated to the existing AC infrastructure. And here we can also see that we can use the solid state transformer again, but we can cut some components, and we have the same functionality. The advantage here is an increased efficiency, because all of these components, like charging infrastructure, always have a rectifier, which we wouldn't need with the DC underlay grid. We will shift basically the rectifier to a central rectifier, and we have shown in several projects that this is increasing our or decreasing the CO2 footprint, and also increasing the net present value of our installation. So to show this here, how the solid state transformer would look for a DC underlay grid and which components would be omitted here. It's basically one of the AC-DC stages, and I also put some axes here on which components would be not necessary in such an installation. And we can see that the size of the solid state transformer can be reduced by about 33%. And also the material consumption is reduced by much more, because this large LCL filter in the bottom is not needed anymore. So these all also weigh very much, and I think I couldn't even lift this one up. So it's around 200 kilograms, I think. So it's a lot of a lot of material in these filters. And using the DC underlay grid, we can get rid of this part. Yeah, and if we go to full DC grids, we can even get rid of more, because we can then also omit the other AC-DC stage, and yeah, the size can be reduced by more than 66%, just an estimation. Yeah, with this, we basically have the DC transformer, or as we sometimes say, Edison's missing link. So if Edison 130 years ago had the dual active bridge, we might be using DC grids today and not AC grids. But obviously this is a much newer innovation. And we're also doing some projects here to support exactly this. Stability is also an issue in DC grids, not only in AC grids. And also the protection is currently under investigation, and we are building an LVDC living lab here in the project Shift to DC, which is a large EU project where we demonstrate an industry or where we have an industry demonstrator. We also work closely together with E.ON here, for example, where we demonstrate radial DC grids. So this is also one of the advantages of DC. We can build radial grids, so ring structures, and with this we can increase the availability of this grid. And this will be done here at our test hall, or in front of our test hall. And we build basically 140 meters of LVDC grid here. It's yeah, demonstrating the LVDC underlay grid. And also DC Link, where we will support, or we are supporting standardization and installation. We are working closely together with Current OS and ODCA, where we are both memberships. And also we're building a lab where yeah, technicians can learn how to install DC equipment, and also where component manufacturers can bring their components and test after exactly these standards which are currently proposed. And we are developing basically the test procedures to test these components for DC grids. And also the research campus Flexible Electrical Networks is one of the major demonstrators here. We already have the 5 kV MVDC underlay grid, which we installed in 2019. And now in the third phase of the research campus, we will be putting one of the lines into full operation. We will install new converters here. And then we can have active power flow control between the two substations here, Laurensberg and Campus Melaten. We are working together with Regionetz with this. And additionally, we can apply or we can supply power to different test benches here at the Research Center Karl, at the new FEN building, which will be built or which will be finished hopefully mid of 2028, and also in the new Fraunhofer building. Also, we are working on market transfer. So with the city of Erkelenz, for example, this week we had a talk with the mayor again regarding new installations here in Erkelenz, which is yeah, slightly north of Aachen, close to the lignite mines for several lignite brown coal power plants here in North Rhine-Westphalia. And there are some villages which should have been removed, but RWE said we are not, or we don't need this lignite there, so the city can buy them back. And also the infrastructure which is currently there can be bought back by, in this case, NEW. And they are also looking into DC. They came to us asking us if we can help them install DC. There's a future-proof solution to support the existing AC infrastructure, so that they don't run into the same issues which currently a lot of DSOs are running into, especially in urban areas. Yeah, we have several institutes working together on this and supporting the city of Erkelenz here. Also Euskirchen, the company Eugebau, who built basically social housing in Euskirchen. They bought a new district around an old slaughterhouse. Here's a schematic shown. There will be a lot of housing. I think 75 or more apartments will be built there. And they also want this supplied by a DC ring bus system, and not the apartments themselves, but the PV and the central heating and also the batteries and EV charging should be connected to this DC system, and they are planning a central rectifier here to supply exactly this DC grid. Yeah, so to conclude, we have new prosumers in the low voltage AC distribution grid, which are a big challenge for the distribution grids. And solid state transformers offer a retrofit solution for horizontal grid coupling with active power flow control to basically shift the loading between different grid sections. And we also have a demonstrator at PGS where we demonstrated exactly this with 250 kVA with a high power density medium frequency transformer and new control strategies. And we have seen that DC grids offer several advantages for new installations. For example, higher efficiency, lower material consumption, and we can support the existing AC distribution grids. Yeah, and we have several projects demonstrating DC installations, and we are pushing market transfer with several companies. And here are also some of the project logos shown here, where also several institutes are involved from E.ON Energy Research Center. Yeah, thank you very much for your attention.
Thank you very much for this presentation. So I think we have still about 5 to maximum 10 minutes for questions. And I think there have been some questions on the chat coming up. And maybe the speakers can come to the front here to answer maybe some of these questions at this point.
Yeah, there are not too many questions yet, but you may still raise questions. So the first one was probably to Mr. Schwarz, and this was about regarding the blackout in Spain. Does an implementation of grid forming converters also solve the voltage problem and therefore the stability concerns?
Yes. In general, I think that grid forming converters, or in general inverter-based resources that are power electronics driven, have way more capabilities than classical assets because they can react much faster. They are much more flexible. So they are definitely a part of the solution. However, the challenging part here is if we have multiple of these grid forming assets or different inverters, how we can coordinate them. Because the system classically was not meant to be, let's say, controlled or regulated by distributed type of assets. And I think that is the key challenge, to ensure that we don't have contradictory control decisions. You want to? Sorry. Okay.
Yeah, so at the end, you need maybe in a region a powerful grid forming converter, and the others should follow, right?
That can also be an opportunity. Yeah.
All right. Okay. Maybe a question to the second presentation. So I did not really understand, why do we need these transformers when coupling the low voltage grids? Switches is okay to decouple in case of failures, but why transformers?
Yes, the transformers are there for galvanic isolation, because if I just install two inverters there back to back, which is done, for example, in a wind turbine, we can get circulating currents between the two AC grids through the start points of the transformer. So it's very challenging to basically keep these circulating currents very low. And the easiest solution then is to install this central galvanic isolated transformer and like this cut the path for the circulating currents. Okay. And also it offers several advantages for protection. Lightning protection, for example, yes.
Yeah, but this could be done by switches as well. Well, that's the idea of a fuse at the end of the day.
Yeah, but the fuse has to be replaced and the transformer is always operated. So it's designed to withstand lightning, and like this, we can basically, if one section is struck by lightning, then the other section is still can be operated without any issues.
All right, so I don't see other questions in this chat. Are any questions in the room, maybe? Yeah.
Thank you for the very good presentations. I would have a question on the energy density of the transformers, more the second part. And you referred to the gravimetric energy density a lot and said how much weight difference is there between the assets. I often heard that it's in practical, the weight is not that much of an issue. It's more about the volume. And then I often heard the critique that solid state transformers actually still host a lot of volume because you have also the additional devices that you need. So overall, you do not even save that much in volume, but you might get additional issues in terms of reliability and so on. So that's a bit the critique that I often face or hear on this topic. So maybe you could elaborate a bit on that.
Yes, that's also one of the challenges I had on the slides, where I said we have more active devices, and reliability is obviously one of the key factors, or one of our research focuses, where we also investigate how to make inverters more reliable, how to do also monitoring of the devices online. So that's also one of the advantages of such a system. We can do online monitoring because we have controllability and also usually some form of communication. And if we already see that one component might fail in a very short time, we can do some predictive maintenance, and someone can already drive there and replace the component before it fails. This is what we do at Karl. So we do it for power electronics, and Professor Sauer does it for batteries there. And the other issue for the power density, the volumetric. So yeah, obviously the prototypes, they have a lot of air. We can see this. It's very empty inside these cabinets. But in the end, we could also build this very power dense. And we do this, for example, in charging stations or in electric vehicles where we don't have a lot of space. They have very similar components to a solid state transformer. So 300 kilowatt charging station is also quite small and much smaller than the prototype I've shown. And we could basically build the same thing in such space.
I would like to add that we also build this with redundancy. They will never fail. Like in HVDC.
Just one very short question on this. What is the difference in efficiency between a classical transformer and the solid state transformer?
So this solid state transformer, we built it with IGBTs, so not state of the art. I think we got to around 96% efficiency with this one. So AC to AC. I think we can increase this with silicon carbide, and as a reference, a normal isolation transformer also only has a peak efficiency of 96% in this range. And especially at low loads or no load conditions, the solid state transformer is better because we don't have to switch. We can switch them off, the passive transformer is always connected to the grid, and also it has some losses even when no current is flowing through it.
But it means at the end, the amount of heat which have to be removed is pretty much the same.
Yes,
because this has something to do with volumes.
Yes, the heat is basically the same.
Basically the same. All right, so I think we're at the end of this first session. We have a short break. We will return at 10:30, right? And for those who are in the room, who are here, there are some buns and something to drink. And those who are sitting at home, you have to be alone with yourself. And next time you can join us.